So now we are going to start off with the unit of unification scheme, and today in the first lecture we are just going to have a brief overview of what exactly do I mean by this. I think in the previous lectures of nuclear physics we have already talked about it briefly, but now we are actually going to specifically talk more about the electroweak interaction or the grand unification theory. Okay, and then when we look into it, we are also going to see some more aspects of the same, some reactions which are weak, some reactions which are electromagnetic, how do we combine them, why do we combine them, and so on. Okay, so this is the first lecture, and then in the first lecture let's just try to revise a bit. Okay, so we are not going to have a very long lecture, this we are going to have a bit of revision because these are the things which we know from before. So a key process in the early universe is the unification of the fundamental forces. Now we need to just recall one fact, that all of these unification theory, whatever has been shown here, is not proved. Okay, it's very difficult to prove such theories. For example, the grand unified theory or the supergravity, all these things are till now theoretical. Okay, and even the electroweak force is more or less combined, and then we have do have some proof of it. Okay, so before we start, what are the four forces we are talking about? Is nothing but the gravitational force, and then we have got the weak force, and then we have got the electromagnetic force, and then we have got the strong nuclear force. So in all of these forces, one of the most important fundamental concept is nothing but the exchange particle. As time has gone on, it has been more difficult to detect these fundamental particles, but we do know that when we are talking about the nuclear force, which is the strongest force known, the exchange particle or the exchange boson that we have is nothing but the gluons, right? So we already know these are nothing but the gluons. When we come into the electromagnetic force, we are concerned more about photons. So gluons, photons, they are more or less detected, so the chances are that we know about them. Okay, and then in the weak force, even the W and the Z bosons that we are talking about are also detected. But in gravitational force, something which we call as graviton is something which is yet to be detected, but theoretically there must be an exchange particle, since the other three kinds of nuclear force does have the exchange particle. So these are exchange particles or exchange bosons, and under this we have got the gluons, the photons, the W and the Z bosons, and the graviton. The three WZ boson and the gluon and the photon has been listed in the standard model. So if you talk about the standard model, that also talks about the exchange particle, which is also fundamental in nature. So this is what we have already read. Okay, and the problem here is that before the unification point, okay, before the forces were unified, okay, the forces were indistinguishable and had symmetry, but after the unification the forces act differently and the symmetry is more or less broken. Okay, so we just need to look into the symmetry part also. We are going to look into it in more detail in the later classes. So what happens is, if we have the weak force and the strong force and we are actually trying to study them together, we combine them into a single theory, which is nothing but the electroweak force. Now the exchange particle WZ boson, or let it be the photon, exists at different energies. So what kind of energetic system you have, depending on that you have got these exchange particles. So at some point the energy at which the WZ bosons or the photon exist more or less should have a similar energy, and as such we can actually combine them. Okay, and a similar logic also exists when we actually combine the electroweak force with the strong nuclear force, and then we have got something which is called the GUT, the grand unified theory. Now this is again theoretical, there are not experimental proofs there. Okay, and finally when we actually combine all four of them, if we are interested to combine, we basically call upon the super gravity, or we usually call it as the quantum gravity. Now this has been the most difficult task, because this is something which will be more challenging, because the graviton is a kind of exchange particle which is not yet discovered. So whenever we're talking about unification, the bottom line is that we are trying to unify matter and energy. So we are talking about matter and energy, and from Einstein's equation we know that matter and energy are interchangeable. So this relation E is equal to mc square is also relevant when we are talking about the unification process. Whatever we see around us, which is basically taking kind of structure or shape, even the dark energy or the dark matter as such we're talking about, is also having some kind of energy involved. Okay, and whenever we have got some kind of energy, we cannot get away with the fact that there is also an involvement of force. So whenever we say matter, these are actually held together by the force. Okay, and that force is nothing but the four forces that we are talking about. If you remember, in our nuclear physics and the particle physics class, I did talk about the origin of the universe, and when we say that the universe exploded, okay, uh, it was very much contracted to a very small minute point, and at that point all the forces must have been acting there. So the gravitational force was holding it tight, okay, and then we had the electromagnetic force because it had got that energy involved. We had the nuclear force because ultimately from there we got the nuclei and all, okay, and then definitely we also had the weak forces, okay, because of detection of other elementary particles. So all these basically makes a logic that when the universe began, or just before the point where the universe was about to begin, all these four forces were together. Now of course we don't really understand that how they are together, or it becomes difficult to put them in a mathematical framework. So let's talk some finer points here. So example of unification is considered the interaction of the weak and the electromagnetic forces. So the first idea of unification actually came from the electroweak interaction. So that means if we combine the weak and the electromagnetic forces, we get the unification. But the point here is that why people did think about this. Okay, so for this we have to just consider 2 points. The first point is at low energy, okay, then the energy, by low energy we don't mean something which we can actually see in our day-to-day life. Okay, it depends on what kind of system we are considering. So at low energy, the photons and the WZ particles are the force carriers of the electromagnetic and weak forces. So if we consider the lower energy, basically the particles which we actually there is exchange are photons and WZ particles. The point here to note here is the low energy term. Okay, now what happens is this W and Z particles are very massive, okay, in terms of nuclear scale or the atomic scale, and basically requires a lot of energy. E is equal to mc square. Okay, now this is where the WZ particle and photon are connected. That means at the energy which is required. Okay, now when we consider photon, the same energy or a similar energy is existing with which is comparable to W and the Z particles. So at high energy, even photon has got a similar energy, and then you can say that the forces will become unified into electroweak force. So if you consider a high energy system, that means when the universe was about to begin, that was a very high energy system. Definitely the photon and WZ particles actually had similar kind of energies involved, because of which their unification can be thought of. Okay, so it's a very simple concept. Please try to understand this slide. At any point if you find it difficult, just pause the slide, write it down, and then try to understand what exactly the sentences mean. Okay, so there is an expectation that all the nuclear forces of matter, the strong, the weak and the electromagnetic, unify at extremely high temperature. So we already seen the logic behind why weak and electromagnetic will combine at higher temperature. Even the strong force, when we have the gluons, can exist at higher temperature, and then we can combine all three of them, and this is something which we call as the grand unified theory. Okay, so please remember the term theory, because we are talking only about theory right now. Okay, no experimental proof as such. So this is basically the grand unified theory, that is an extension of quantum physics. Okay, so we go deep into quantum physics and we understand the operator and all the functions, the wave functions and everything, and then we use all these concepts together. We also look into the logic of tensors and all. Okay, and then use all these logics together to actually combine and form a mathematical formulation. And this is an extension of the quantum physics using an yet undiscovered relationship. So, this relationship between strong, weak and electromagnetic force is not yet discovered. Okay. So, that is very important. So, we need to people need to work on this, the scientists are still working on these kinds of things. Okay. So, the final unification resolves the relationship between quantum forces and gravity. And if we look into the final relationship, a long way to go, because we are still to detect gravitons. But this will actually talk about the unification of quantum forces and gravity, and usually we term that as nothing but the supergravity. Okay, so that is the supergravity theory. Now, in the early universe, the physics to predict the behavior of the matter is determined by which forces are unified and form that they take. So, the universe, how it was formed. Okay, if we want to actually predict and we want to understand the physics behind it, we have to know the behavior of the matter. Okay, and which matter actually was controlled by what kind of forces and what are the forces that were acting on that particular matter. Okay, so in the next class we are going to talk more about the electroweak forces and all. Okay, now let's just have a look at this graph. I think this is something which we have discussed, but we have not represented it graphically. Just let's have a look at this. Okay, along the x-axis we have got the age of the universe. So this was the beginning of the universe, and this is where we are today. Okay, so this is where we are today. Okay, on that time scale, I think whatever lifetime we have is very short, and this is the temperature which existed. So we know that if the temperature is too high, as we talked about, the universe was too hot, and then we didn't even have hydrogen. We just had protons and neutrons moving out separately. Okay, at some point, and then we understood that there were quarks and so on. So all these things was predicted, and at the very beginning, when the age of the universe was just 10 to the power minus 43 seconds, so we actually had something which we call as the okay, let me just zoom in here. Okay, so we actually had something which is called the space time foam. Okay, and then when the temperature when we are talking about 10 to the power minus 35 seconds, the temperature reduced. So you see there is a linear decrease in time. Okay, so then we actually had the quark leptons, which actually created the inflation. So I'm going to tell you what is inflation all about. It is basically nothing but the reason because of which the universe is expanding. So inflation of the universe in short. And then in 10 to the power minus 12 second, we actually had the four forces established, the lepton. Okay, and established, and lepton splits into neutron and electron, and gravity governs expansion, and gravity will basically govern the expansion. Okay, okay. Then we had 10 to the power minus 6 second, and we had got quarks, which actually made the protons and the neutrons. So at the 10 to the power minus 6 second, proton and neutron came into the existence, and then in the first second actually we had the neutrinos decoupling, and then as time went on, at the 15th second, electrons and positrons annihilate to leave small numbers of unmatched electrons. So there was annihilation, but still there was existence of electrons, because if there was electrons, if there was perfect annihilation, and if we talk about the baryon anti-baryon symmetry and not asymmetry, then the universe would be just nothing but an empty space. Since there was an asymmetry, so there was some kind of baryons were left out even after annihilation. And then in the first minute, the fusion of hydrogen and helium occurred, and then after a good old 500 years, okay, 500 years, so we actually had the, okay, we'll just, so after 500 years, we actually we had the photons, which is decoupling, and then we finally had the CMB radiation. Okay, so we had the cosmic microwave background after not 500, sorry, it should be 5000. Okay, so it's 5 and 50, so that's 5 lakh years. Okay, and then 13 billion years later, which is today, we actually have the galaxies, the stars and the suns and all, whatever we have, whatever we can see. Okay, whatever exists. So in that time scale, we can say that 13 billion years is nothing but today itself, because it's a very small time scale in which the earth has existed compared to the birth of the universe. Okay, so this is the graphical representation. I hope all of you can get this. Please try to understand this better. Okay, there are some more information, like this was the slide which I have shown at the beginning. Okay, and then the black holes actually had part of the, it should be having graviton, lepton and quarks involved. Okay, and then we have the involvement of photons, talked about neutrino, antineutrino and so on. Okay, and the quarks are nothing but it came out to be proton and neutron, which actually had the quark combination and so on. So these are all self-explanatory in this graph. You can look into this graph, okay, and then have a clear idea on this. Okay, so what I can do is I can just remove all the markings so that you can take a screenshot of it and try to understand it better. If possible, you can just draw it in your copy as well. So since I use the term inflation, let me just talk about this. So we talk about inflation in physical cosmology. Physical cosmology, as I told you before, is nothing but a theory which talks about how the universe originated, what's going to be the future, what was the past, was there a big bang, and so on. Okay, so all these questions. So we basically call it as cosmic inflation, or we call it cosmological inflation, or we just call it as inflation, just inflation. Okay, so it's basically a term which is also used in economics. So if you search it on net, you basically prefer writing inflation cosmology, so you can get more information on this. Okay, so the theory of exponential expansion of the universe of the space in early universe. So the space expanded in early universe, and that is termed as inflation, as simple as that. But remember the term exponential, it was actually increasing drastically. Now this inflation actually lasted from 10 to the power minus 36 seconds. So the universe started, 10 to the power minus 43 seconds passed by, and then when it reached 10 to the power 36 seconds, it started expanding, okay, after the Big Bang singularity to some time between 10 to the power minus 33 and 10 to the power minus 32 seconds after the singularity. So within this time range, the expansion happened. Okay, and then following the inflationary period, the universe continued to expand, but at a slower rate. So at that particular point, it was expanding very fast, exponentially, but then after that, it is expanding. It is still expanding today as per the work done in 1990s and using the Hubble telescope. Definitely it's still expanding, but then that is at a much slower rate compared to that actually that happened at the beginning of the universe. Now the acceleration of the expansion due to the dark energy began, okay, after the universe was already over 9 billion years. Okay, so after 9 billion years, the dark energy contributed to the expansion of the universe, which we believe is still contributing to the expansion. So in the next class, we are going to look in more detail and closer to the electroweak force. So that's all for today. Thank you.